In this video, I want to talk about multiplexers and decoders and how they can be useful in implementing Boolean functions. Multiplexers are one of the building blocks of digital logic circuits that can be used to select between one out of n inputs that we may have. So if you remember from before, we said that if we have, let's say, 3 bits to represent a number, we have 2 to the power 3 or 8 possible combinations for this number. So anything between 0, 0, 0 all the way to 1, 1, 1 could be represented using 3 bits. So now this n that you see here is practically the total number of possible cases or combinations that we can have. So if I chose this number of bits as n, we can have 2 to the n equals capital N here. And that is the idea that we work with here. So to be able to do that using a multiplexer, we need to have some select or control inputs. So how many select or control inputs do we need? The answer to that is log 2 of n. So in this equation, you see we have 2 to the power of lowercase n to be equal uppercase n. So now if we calculate log base 2 of n, or log base 2 of 2 to the n, the answer would be lowercase n. So what does it mean? It means that if we want to, let's say, choose between 2 inputs, that means that we need to have lowercase n or the number of select or control inputs to be 1. What about if we want n to be 4? Keep in mind, uppercase n here is always the power of 2. So we cannot have n equals 5. So let's say if n is 4, that means that the lowercase n is going to be 2. What about if n is 64? Since 64 is 2 to the power 6, that means that we need to have 6 control inputs to be able to select between all the possible combinations. So let's just take a look at a basic multiplexer that gives us the capability to choose between 2 inputs. So we have here 2 as the number of inputs, and then we have 1 which is the number of outputs. So in multiplexers, this is always 1. So the number of inputs can be different. So it can be 4, 8, 16, all the way to the value that we want. Again, this is a power of 2, but the output is always 1. So we always choose one of the inputs and deliver it to the output. This is the way that we show a multiplexer symbolically. So as you can see, we have here for a 2 to 1 multiplexer, we have D0 and D1 as the 2 inputs. We draw the multiplexer as this trapezoid shape, and then we have the select input, the single select bit input that we need here coming from the top. Here I called it S, and then we have the output, which is Y. So as you can see here, we have, for this simple multiplexer, we have 3 inputs, 2 data, and one control, and we have one output, which is basically whichever of the D0 and D1 that according to S we are selecting. So if I want to write a truth table for this multiplexer, since we have 3 inputs, that means that we need to have 8 possible combinations. So I put them in this order. We have S, D1, and then D0. And then, since again we have 3 inputs, I wrote down the 8 possible combinations that we can have, starting from 0, 0, 0, all the way to 1, 1, 1. Again, this is ordered, so everything is more streamlined and more consistent, and to reduce the confusion. You can have this table without proper ordering of the rows and it works fine, right? But if you have it in order, that makes everything more consistent and less confusing. So now the way the multiplexer works is that depending on the value of S, is either choosing D0 or D1 to be delivered to the output. So we define it here as when S is 0, like for these 4 rows, the value of Y equals the value of D0. So you can see when S is 0, Y equals 0 when D0 is 0, and Y equals 1 when D0 is 1. So you see, it looks as if the value of D1 doesn't matter, right? Whether it changes or not, we don't care. As long as S is 0, Y equals D0. For the other 4 rows, when S equals 1, Y equals D1. Again, in this case, we don't care about the value of D0 when S is 1. So since we have this, we can write this truth table in a much shorter and a smaller version, basically saying that when S is 0, Y equals D0. Of course, D0 can be either 0 or 1. And when S is 1, Y equals D1. Again, it means that D0, D1 also can be both 0 and 1, right? So basically, to wrap the definition around completely, we can say that S, the select or control input, is basically selecting whichever of the inputs to be delivered to the outputs. So now you might say, how can I implement a multiplexer or create a circuit that acts like this? And the answer to that is very simple. I have talked about several different ways that you can go from a truth table into a Boolean equation. So let's just try a couple of them. The first approach is based on the sum of product form. So if you remember, we said that we will be looking for the rows for which the output is 1, and then we OR all the mean terms associated with those rows. So if I do that, Y would be equal to, what is the mean term associated with this? It's going to be S bar, D1 bar, D0, plus S bar, D1, D0. So this is for this row. Then plus, for this row, it is S, D1, D0 bar, and then finally for the last row it is S D1 D0. So as you can see, we can simplify this equation. So between the first term and the second term, S bar D0 is common. So I can take it out. S bar D0, we factored out, and then we end up with this term. And for these two, S D1 is common between the two, so I factor it out. So I end up with S D1 plus multiplied by D0 bar plus D0. As you know, again, this equals 1. This also equals 1, which makes the final function to be S bar D0 plus S D1. As you can see from this equation, when S is 0, which makes S bar to be 1, this term equals D0, and this one equals 0. So when S is 0, Y equals D0. And on the other hand, when S is 1, which makes S bar to be 0, Y will be equal to D1. Basically, this table itself. So based on this, we can write the Boolean equation using this truth table as well. So even though in this truth table we have Y to be D0 or D1, which we didn't cover before, you can think of it this way. In the sum of product form, we are basically writing all the minterms for which the output is 1, right? You can think of it this way. We basically multiply the minterm with the output. If the output is 0, that means that we are not going to include it, right? If the output is 1, that means we are including it. So if I want to write this in its full form, Y would be S bar D1 bar D0 bar multiplied by 0. You see, this is the 0 that we have here. And then for the next one, S bar D1 bar D0 multiplied by 1. This is for the next row. And then so on and so forth, right? If I continue this for all the 8 terms, basically for the ones for which the output is 0, these will be cancelled out, right? So that's why when we write it in sum of product form, we don't even bother to include these, because we know that the output for this is 0, so the result here is 0. For this one, if we want to write the sum of this short version of the truth table using sum of product, we basically do it like this. We write the associated minterm for this row and we'll multiply it by the output. So since we don't know what might be the output, we just use it itself. I should clarify that this is basically an AND. I just put it as multiplication for a little more emphasis, right? So if we do that, the minterm associated with this row, it is going to be S bar, and then we multiply it by D0, or we AND it with D0. For the next row, the minterm associated with this is going to be S, and then we AND it with D1. As you can see, this form, I call it form 2, and this one are exactly the same, right? So it doesn't matter whether we go from this truth table to the equation or from this one. They both result in the same equation. There are other ways to do and come up with the Boolean function too. The other way is the product of sum, which I highly suggest you do it on your own. What about the Carnot maps? Right? We said that if we use Carnot maps, we can do the simplification much more visually, right? And that is true here too. So let's just say we want to come up with the Boolean equation for the 2-to-1 multiplexer using the Carnot maps. So the way I did it here is that I created a 2x4 Carnot map. I separated the variables. I used S to show the rows, and I used D0 and D1 to show the columns. Here, as you can see, for the columns, since we have two variables, we have 4 possible combinations. Again, since we want to have only one change when we go from one cell to the next one, I used the gray code to represent the columns. So not the regular counting from 0, 0 to 1, 1, but the gray code for counting using 2 bits. So we have 0, 0, 0, 1, 1, 1, and 1, 0. And then after we create the blank table, we fill it out using the previous truth table. Then we start looking for circles that contain the cells with values of 1. We try to go as big as possible, as large as possible for the size of the circles or the number of cells in the circles. So here, as you can see, the largest one that we can create is of the size 2. And then we write the term or the implicant for each one of these circles one by one, and we OR them together. So if we do that, if we follow these steps from a previous lecture, we come up with this final function that is the equation for a 2-to-1 multiplexer. So now that we have this equation, implementing it using logic gate is very straightforward. We have D0 and S bar to be ANDed together, D1 and S to be also ANDed together, and the result of these two ANDs is going to be ORed. So we have D1 ANDed with S itself. So this creates the D1S. We have D0 to be ANDed with S that passed through an inverter. So here we have S bar, and here we have D0 S bar. And then now finally we have these two terms that go through 1-2 input OR, and then it creates the final function for the 2-to-1 multiplexer. But this is not the only way to implement multiplexers too. Another way of implementing multiplexers is by using tri-state buffers. So if you remember from before, we said that tri-state buffers are buffers that have a control input as well, or an enable input as well. What does it mean? It means that it determines whether the buffer is even on or off, right? So now, since we want to create a 2-to-1 multiplexer, we can use 2 tri-state buffers. One gets the control signal itself, and the other one gets it inverted. So this bubble, if you remember from before, representing the inversion or the complement operator. So if S is 1, that means that S bar is 0. That means this tri-state buffer is off. But the second one is going to be on because S is going to be 1. So that means that this tri-state buffer is on, and it passes D1 through it to its output. On the other hand, if S is 0, this tri-state buffer will be 0 or off, and the first one will be on, because if S is 0, that means that S bar is 1, that means this tri-state buffer is on, and the 0 would pass through from the input to the output, which is Y. And as you can see, this way of implementation is going to be much more simpler than using the Karnaugh maps. Why? Because let's say if you want to have n inputs, we only need to use n tri-state buffers. Of course, we need to control the select input and connect the proper select input to each one of them individually. But the implementation would be simpler than implementing using logic gates. Or like going through the Karnaugh map, coming up with the Boolean equation, and finally doing the implementation using logic gate. So now that we saw this, the question is how multiplexers can be useful. And the answer to that is that they can be used as lookup tables to implement Boolean equations. So let's just go over this quick example before I go to the multiplexer based implementations. So we have A and B as the two inputs, we have Y as the output. So we have input here, we have output here. Since we have two inputs, there are four possible combinations that we can have: 0, 0, 0, 1, 1, 0, 1, 1. And for the output, for this random function, Y is 1 when both of them are 1. You remember from before that this means that the function is an AND function, right? When both of the inputs are 1, the output is 1, otherwise it's 0. So going from this to the Boolean equation, if we use the sum of product, we have Y equals AB, right? Because we only have one minterm for which the output is 1, and that minterm is AB. So now if you want to do the implementation, we can do it like this. We have A, B going through an AND gate to create the output Y. But what if we don't have access to individual gates? Because that is always a possibility, right? Or what if we want to change the function kinda on the fly, right? If we want to go through several different functions, we cannot have all those functions that we want implemented, right? One of the ways is to use the multiplexer. So basically you can think of the multiplexer as a lookup table. You kinda provide some input to the multiplexer, and then depending on the situation, you choose any of the inputs to be delivered to the output. Actually, implementing using multiplexers is very straightforward and very simple. You basically copy the pattern of the truth table onto the multiplexer. So let's just see how it can be done. So first of all, you see here that we have two inputs or four possible combinations. So if you remember from the previous equation, we had 2 to the lowercase n equals uppercase n, or log base 2 of n equals lowercase n. That means that for this function, we need to have two control inputs. So here, lowercase n equals 2. And these two control inputs are exactly the inputs that we have in the truth table. So out of the 6 inputs that this 4-to-1 multiplexer has, 2 of them are already determined. The control inputs are the inputs to our circuit. What about the other 4? Or what about the possible outputs that we want to connect to the, possible inputs that we want to connect to the output? Or in another word, what are the inputs that we want to select from, right? So what happens if A and B are both 0? So when A and B are both 0, the 0, 0 input is being selected. What is the value for A and B being 0, 0? The output is going to be 0. So in that case, that means that this input needs to be connected to the ground. So this is the symbol that we will use for the ground. And you saw it before when we were implementing logic gates using transistors too. So this means that anytime A and B are both 0, the 0, 0 input of the multiplexer will be selected, and that 0, 0 input is connected to the ground. So ground is 0, so that means that Y becomes 0. What about when A, B are 0, 1? The second row. In this case, the 0, 1 input of the multiplexer will be selected. Again, since the output should be 0, we connect that one to the ground as well. So if you remember before, I said that when we have 3 wires selected at a point, even though we don't have a point there at the location of the connection, that means that they are still connected, right? This one meant that they are not connected. This one is connected, so not connected, connected, and also this one means that it is connected. So what about when AB is 1, 0, the third row of the truth table? In this case, again the output is 0. So we connect that one also to the ground. And finally, for the last row, we have A and B to be both 1s. So when both of them are 1, that means the 1, 1 input of the multiplexer is going to be selected. Since we want the output for this case to be 1, that's where we can connect this to VDD or VCC, or in another word, 1. So the ground has a symbol like this, and VDD or VCC have a symbol like this. Again, these are the things that you have seen it before. So just by doing that, connecting the inputs of the multiplexers to proper values, either ground for 0 or VDD for 1, and also connecting the 2 inputs to the function to the select inputs of the multiplexer, we can implement the function using a multiplexer. And this thing can be extended or can be changed much easier than coming up with the Boolean equation and then implementing it using gates. So let's say if you want to implement a 2-input OR gate. So A, B, and then Y, 0, 0, 0, 1, 1, 0, and 1, 1. So for the OR gate, if you remember, when most of them were 0, the output was 0. But for the rest of the truth table, the output was 1. So if I use, let's say, the sum of product, I need to go through the rows of the truth table, find out which ones are 1, and then write down the mean terms associated with each one of them and write down the final function. So Y would be A bar B plus A B bar plus A B. So this is basically the OR function using sum of product. For this one, the easier function was to use the product of sum because we have fewer number of zeros than the number of ones. So if we do that, y would be equal A or B, right? So if I want to implement this, I need three 2 input AND gates and 1 3 input OR gate. For this one to implement it, I needed only 1 2 input OR gate. But what if you only had access to a 4 to 1 multiplexer? In this case, you can draw the multiplexer like this. You connect A and B to the select inputs, and then we have 4 regular inputs too. So 0 0 0 1 1 0 and then 1 1. What is the output when A and B are both 0? As you can see here, the output is going to be 0. So I basically connect this to the ground. What about the rest? The output is going to be 1 when either of the inputs or even both of them are 1. So what I do is that I connect all these to VDD. And simply by doing this, I can create the implementation for this function using a single multiplexer. It is possible to reduce the size of the multiplexer that we want to use. So for the previous example, in the previous slide, we used the 4 to 1 multiplexer. We can use a smaller multiplexer too, and the way to do it is very straightforward. Instead of connecting either 0 or 1 to the inputs of the multiplexer, we basically use one of the regular inputs, one of the select inputs, basically A or B, and connect it to one of the regular inputs of the multiplexer. So how can we do that? We need only to see what is the situation of the output, the value of the output, given only a few of the inputs. So let's just see how it works in practice. We have the previous truth table. We have A, B changing from 0, 0 to 1, 1. We have Y, which is either 0 or 1. So what basically we do is that we divide this truth table into 2 parts. We consider this basically the least significant input or the least significant bit in this order, and we separate it from the rest. So here the rest is only 1 bit, but that works for any number of inputs. So if you, let's say, have 3 inputs, which makes the function to have 8 possible combinations, you consider the least significant bit and then separate it from the rest of the inputs. I will show one example later. And then we write the output based on the value of the least significant bit. So let's just see what happens. For these 2 rows, right, for which A is 0, for both of them, what is the relationship between Y and B? As you can see, Y is always 0 for these 2 rows. So that means that it doesn't depend on the value of B. When B is 0, Y is 0. When B is 1, Y is still 0. So in this case, we can use it like this. We say when A is 0, Y is 0, no matter what the value of B. Now let's do it for the next set of 2 rows. What happens when A is 1, which is true for both of these rows? For these 2 rows, when B is 0, Y is 0. When B is 1, Y is 1. So that means that for these 2 rows, 1 equals B. So now that we have this, let me just quickly draw the previous implementation that we had using the 4 to 1 multiplexer. So we had these 3 inputs to go to the ground, and this one to go to the VDD. So it was 0, 0, 0, 1, 1, 0, and then this one was 1, 1. So this one is using a 4 to 1 multiplexer. For this one, we reduced the size of the multiplexer by a factor of 2. So here we did the same implementation using a 2 to 1 multiplexer. So here, as you can see, only variable A is chosen as the select input. And depending on the variable A, we either choose 0 to be delivered to output, or we choose B to be delivered to the output. So let's just go over a larger example. So let's just assume we have this truth table with A, B, and C as the inputs, and we have Y as the output. So we have 0, 0, 0, 0, 0, 1, 0, 1, 0, and then 0, 1, 1. And then 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Like as I said before, you can create any random function that you want. Let me just create a random function like this. So here is a random function that I just created for this specific example. You can do it the same way too. So let's just say I want to do the implementation using an 8 to 1 multiplexer. So I draw a multiplexer. So to make sure the size is accurate, I just put the inputs here before I close down the design. 1, 0, 0, 1, 0, 1, 1, 1, 0, and then 1, 1, 1. So I close it like this. So we have A, B, and C as the 3 inputs for this 8 to 1 multiplexer. You see we have 8 possible inputs, and then we only have 1 output, which is Y. So now it's the time to connect the inputs, the regular inputs of the multiplexer, either to 0 or 1. So the first one is connected to 0. I just draw it like this. The second one is connected to 1, so I just draw it like this. And this one, there is no connection because there is no dot on these two crossing lines. The third input is again going to be 1. The fourth one as well. Then we have 2 zeros, so 1, 2, another 1 here, and then finally this one is again connected to 0. So this is the implementation of this 3 input function using an 8 to 1 multiplexer. So now let's say we want to reduce the size of the multiplexer using the technique that I just described. As I said, we separate the least significant bit. You can do it for any other bits too, right? You only need to separate one. But it is much easier and less confusing if you do it with the least significant bit. And then we divide the table into rows of 2. Because as you can see, for each row of 2 in this truth table, the rest of the bits don't change. So here, when I separated A, B, and C, so when I take out C, for these 2 rows, the value of C changes, but the remainder of the table, remainder of the inputs don't change. So that's how we can write the function y in terms of the least significant bit. So now that we have done it, we go see what happens for the first set of 2 rows. For these two, A and B are both zeros. Y is either 0 or 1. So what is the relationship between Y and C? So Y can be either equal to 0, equal to 1, C, or the least significant variable in general, or C bar. Which one of these 4 cases here we have? As you can see, when C is 0, Y is 0. When C is 1, Y is 1. So that means that Y equals C here. What about for the next set of 2 rows? When C is 0, Y is 1. When C is 1, Y is also 1. So that means that the value of C doesn't change the value of 1. Y is always 1. So we have Y to be 1. What about for the next set of 2 rows? Here, when C is 0, Y is 0. When C is 1, Y is again 0. So that means that Y is always 0 for these 2 rows. So we have the relationship as Y being equal to 0. And finally, for the last one, last set of 2 rows, when C is 0, Y is 1. When C is 1, Y is 0. So as you can see, Y equals the complement of C. So now we have figured these out, the relationship between the output and the least significant input. So now what we can do is that we can use a smaller multiplexer to do the implementation. So here we only need a 4-to-1 multiplexer. We use A and B as the select variables. And then depending on the value of A and B, we either connect Y to 0, to 1, to variable C, or C bar. So for the first case, when A and B are both 0, Y equals C. So I just draw a line and write C here. So that is my input C. When A is 0, B is 1, Y equals 1. So I just write it like this. I use the symbol for VDD or 1. When A is 1, B is 0, Y equals 0. So I just write it using this, the symbol for ground. And finally, for the last row, when A and B are both 1s, Y equals C bar. So what I do is that I just say C goes through an inverter and will be delivered to this input. So as you can see, going from this to this, we have reduced the number of, basically reduced the size of the multiplexer. Of course, that comes at the expense of having an extra NOT gate, right? But nonetheless, the size of the multiplexer is reduced. So now that we saw multiplexers, let's just talk about decoders. For the decoders, n that I consider here is the number of inputs, and we have 2 to the n number of outputs. Decoders' outputs are called one-hot outputs, which basically means that only one output is high at any given time. So the basic idea behind decoders is very simple, right? Do you remember when I said for the truth table, there is one min term for each row of the truth table? So decoders basically create all the min terms for a set of inputs. So remember we said that if you have 2 inputs, we have 4 possible combinations. If we had 3 inputs, we had 8 possible combinations. If we had 5 inputs, we have 32 possible combinations. So an n to 2 to the n decoder basically gets the inputs and creates all the possible combinations for you. So let's just take a look at a 2 to 4 decoder. We have a 1 and a 0 as the 2 inputs, and we have all these 4 outputs. So the order here does not matter. You can write it as 0, 0, 0, 1, 1, 0, and 1, 1, right? Because this is symbolic. You are not going to be using a physical decoder, right? Physical decoders, depending on the size of the IC, they may have different layout for the outputs and the wires that you need to connect. So we have 2 inputs, A1 and A0, and we have 4 outputs, Y3, Y2, Y1, and Y0. So these are the 2 inputs. These are the outputs that we have. As you can see, each one of them is basically a function of the inputs. What you can do is that you can use the sum of product form to come up with the function for each one of these outputs. So for example, for this one, the min term associated for this row is 1, so that means Y3 equals A1, A0, the end of the 2. What about for Y2? Y2 equals A1, A0 bar. What about Y1? Here is this row. We have A0, A1 bar, A0, and this one is A1 bar, A0 bar. As you can see, these functions each represent one single min term of these 2 inputs. So in effect, the decoder creates all the possible combinations of a truth table. So all the left hand side of the truth table. So if we had a truth table like this, we had inputs in the left of this line and we had outputs here. So this is basically what a decoder creates for you, the left part of the truth table. What about the right part? How can I use decoders to implement any function? You just add a single OR, and then you connect the inputs of that OR to any minterm that you want. So let's just take a look at one example here. So this is the implementation of the decoder. Before I give you an example, as you can see, I use the two-level implementation here. We have a 1 here, a 0 here, and then we have these inverters that create for us the complements of these variables too. As you can see, Y3 is the AND of a 0, a 1. Again, these are not connected, right? Since there is no dot. Y2 equals a 1 and a 0 bar. Y1 equals a 1 bar and a 0. And finally, Y0 equals a 1 bar and a 0 bar. So now let's say we have a function that we want to implement. So let's just say we want to have a function y equals ab plus a bar b bar. If you remember, this is the function for XNOR. So as you can see, this function contains two minterms. So we have A and B as the inputs. The outputs of the decoder are all the possible minterms for these two inputs. Since we want to create AB or AB bar, we only provide A bar B bar, and AB as the inputs of this OR function. So Y is basically AB or A bar B bar. Let's just go over another example too. So we have, let's say, AB, and then let's just say we have Y for the function output. So we have 0, 0, 0, 1, 1, 0, and 1, 1. And let's just say our function is 0, 1, 0, 1. So if I write down this function in terms of the sum of product, it becomes A bar B plus A B. If I want to do the implementation using a 2 to 4 decoder, I have A and B here. I have 0, 0, 0, 1, 1, 0, and 1, 1 outputs here. So each one of these is creating one of the minterms. So this is A bar B bar, the first row. This is A bar B, the second row. This one is A B bar, the third row, and finally A B. My function has these two terms. So I need a two input OR gate. I draw it like this. This is going to be Y. And for the two inputs, I connect it to the appropriate minterm that I have, that I need. So this is 1, and this one is the next one. So this is basically the implementation of this sample function. As you can see, you can easily extend it to larger decoders too. So you can easily create random 3 to 8, 4 to 16 decoders and use it to implement larger and longer functions too. In this video, we learned about multiplexers and decoders in great detail, and we learned how we can implement logic function using multiplexers and decoders.